So first of all, let's review what we learned last week. We are still discussing the baseband data transmission, including the transmitter here, channel here. We have also receiver. And remember that we have box, right? The red box, which includes the transmit filter, receive filter that surrounds the channel such that the channel itself has multipath, and therefore we have ISI, intersymbol interference, but we want to design these two and wrap around the channel such that from here to here we want to make an effective channel, right? And that effective channel from here to here, this is actual channel, but we want to make this effective channel to be perfect channel. This actual channel is never going to be perfect, right? So that we wrap around with these two filters so that we want to make this effective channel to be an ideal channel, right? So the goal is that we want to make this effective channel to be Nyquist channel, but unfortunately Nyquist channel cannot be implemented. Therefore, the best thing we can do is to make this channel, effective channel, to be like pulse shaping type of channel. So that's why you put the pulse shaping filter here, right? In order to shape the pulses. The original pulse here is a rectangular pulse, but we want to design a pulse shape filter here so that we want to make it round, right? That way, we want to limit the transmission bandwidth into our bandwidth, and also we want to achieve an ideal impulse response, like only one path, single path impulse response. So that's the whole story of this effective channel. However, this effective channel cannot be perfect, so therefore still we have a little bit of ISI, the interference, intersymbol interference remaining here, right? So that's why we need equalizer, right? Channel equalizer. So for example here, right? From here to here, we tried our best, but because of the implementation, we still have a little bit of interference remaining here. So that's why we design an equalizer, which is a filter that this filter or equalizer will remove some of the remaining intersymbol interference. So eventually, output of the equalizer should have no interference, ideally speaking. Again, the equalizer, again, this is not ideal, not perfect. So what is really happening is still you have a little bit of interference remains here, right? Things are not perfect all the time, right? So you have still a little bit of interference remaining even after the equalizer. That's what is happening in the actual system. But what we are trying to do is by using equalizer, we are trying to reduce the impact of interference as much as you can. So this is the structure of equalizer, but this structure is the same as the other filter. This is a filter. So every filter consists of how many taps you have. So these are number of taps. In this case, we have 2n+1 taps. Also, each filter, every tap has its own coefficient. So we have a 2n+1 coefficient. So each one is a complex value. So that's the equalizer here. So this is the block diagram picture of equalizer or filter. You can draw a impulse response type of the filter. In this case, let's say if you have 4 different filters, 4 different taps, 3 different taps in this case, 3 taps. For example, actually 3 taps, 4 taps, yeah, 4 taps. It can be actually 3 taps or 4 taps, but let's say 3 taps. 4 taps, actually doesn't matter because the first one is just a multiplication, right? And these 3 are memory. Each one is a memory. So in this case, you have 2n+1 tap, and you have 2n memories. So in this case, we have 3 memories. So you can say 4 taps if you like, but 3 taps doesn't matter. But so these are number of taps. 3 taps, let's say. This is an example of 3 taps. You have W0, W1, W2, W3. Each one of these is a coefficient of each tap. Let's say this is the complex value for each one. So this is a impulse response type of the filter. This is a block diagram of the filter. This is an equation for the filter. So all these are same thing. So that's how we design a equalizer. And this is what equalizer looks like. But when you design an equalizer, number one thing you decide is how many taps do you need. Okay? You need to decide how many taps we need. That's first thing you need to decide. Second thing is you need to calculate each one of these coefficients. This one. That's the second thing. Number of taps, this is pretty easy to calculate. If you have some number of interference, let's say in here in interference you have some number of taps, and equalizer number of taps should be larger than interference taps. So this is pretty easy to get. But how to get this W, the W coefficient, that's a little bit difficult. But the later slides shows you how to calculate the W coefficient. Simply speaking, when you write all the input-output relationship of equalizer in matrix form, so this is a matrix. We want to have this output. This is our target output. We want to make the output of the equalizer to be like this. So this output basically means that only this one has one value, some value, all the other has a 0. So that basically means that your output looks like this. Right? We want to get this output. So this is the output we want. This is the input to the equalizer. So simply speaking, we have equalizer here. This is what we want to design. We have output. Output looks like this. We have input. Input looks like this. So when you draw the input as a block as an impulse response type, this input looks like this. We have a C0, C1, C2, C3, something like this, right? We have C0, we have C1, C2, C3, C minus 1, C minus 2. We have all of this value, right? So those are our input. Some of them may be 0. Some of them. Okay? So if this is our input, we have so many interference, right? Inter-symbol interference. So those signal goes into the equalizer. This W is equalizer tap coefficient, equalizer coefficient. Now the output, we want to have this one. So how do you convert this input to this output? So that's why we need the equalizer. So this equalizer is trying to convert this one to this. Okay, so since this is input, this is output, and this is a matrix form. Input goes into here, go through the W equalizer, we're going to get this output. So in the matrix, we can write it as a CWZ. This is C matrix, W vector, and Z vector. And this is the output we want. This is the input we already have. So we know these two. And we want to find out the W. So W is easily calculated by this, right? By inverse matrix. So that's how you calculate the W. Okay? Then you're going to get this equalizer. So this slide shows you the concept of equalizer. When you look at the whole operation from the frequency point of view, what we are drawing here is a time domain, right? This is impulse response. That's a time domain. But when you look at the same thing from the frequency domain point of view, the frequency response here in the input to the equalizer is something like this. Just an example, right? Because here, at this point, your time domain response looks like this. So therefore, the frequency response has a fluctuation, right? Because here, think about it this way. If everything is ideal, then here, impulse response should be this one. That means ideal, right? That means perfect. In that case, the frequency should be this, right? So this is a ideal time and frequency response. But if that's the case here, we don't need the equalizer because we already get the ideal output here. But unfortunately, that's not the case. What is actually happening is right here, we have some remaining interference in time. So because of these things, we are not going to have a flat in frequency. We are going to have some fluctuation in frequency. That is this one, the blue line. So right here, we're going to get blue line, blue frequency response. What is going to happen in the equalizer is we're going to design the frequency response of the equalizer to be the inverse of the blue. So that way, this red one is the equalizer frequency response. And this red one is actually flipped inverse of the blue. So that way, when this input, actually blue one, input goes into the equalizer, then this blue one is the frequency response of the input. And this HF is the frequency response of the equalizer. That is the red, right? So input-output convolution in time is going to be multiplication in frequency. So you're going to multiply red and blue. And these are inverse relationship. So therefore, those are canceled out, right? So you're going to get flat at the output. So that's why we call this the equalizer, right? This equalizer is equalizing the frequency response. So that's our goal. That's what it's trying to do. This is an example. We have some BPSK symbol here. So you have a +1 or -1. So we transmit BPSK. Go through the filter and channel. Let's say our channel has this impulse response. Of course, this is not an ideal channel because we have a multipath. So given this channel, we are transmitting this BPSK symbol through the transmit filter channel, also receive filter. Eventually, you're going to receive these kind of symbols here. This is receiver, right? You're going to receive this. So put this kind of symbol or received symbol into the equalizer, and this equalizer is again filter. This equalizer will filter out these symbols, and then eventually the output of the equalizer should look like this, something like this. Okay. Now then, this output, equalizer output, now goes into the decision block. Now you're gonna make a clean symbol. Okay? So that's the whole story. Okay. So far, we discussed the modulation, like a BPSK, QPSK, 16 QAM. So we discussed the many different modulation. We also learned about the transmit filter, receive filter, right? And we just learned the equalizer. So we learned all of this, all the way up to the equalizer. So what is remaining is decision block. Okay, this is all the other things we already learned, right? We learned all these things, and we are gonna now talk about this decision block. Okay, the decision block is the last step in the receiver. Okay, so question is, how do you make a decision? We receive this kind of symbol after the equalizer. Now, as a last step, we need to make a decision. So how do you make a decision? What's happening inside this decision block? So that's what we are going to look at. So how do you make a decision? In order to understand the decision block, we need to understand some theory, basic theory. One of them is a probability theory. Okay, so let's let's take a look at a little bit on probability theory. So probability theory always starts from uncertainty. Okay, uncertainty. So we have many in real world, in real life, there are so many uncertainties. Let's think about the weather. How do you know what's going to be the weather tomorrow? You never know, right? Maybe you have a guess. Oh, this is some springtime, wintertime. Summertime. So it's very unlikely that you're going to have a snow tomorrow, right? It's very, very rare. Maybe probability is almost zero. It's always probability. What's the probability that we're going to have rain tomorrow? Maybe 10%, 20%. That's always probability, right? So every time that you have uncertainty, you always have a probability. Right? So let's say you buy a lottery. Then what is the probability that you win from the lottery? That's always the probability. Always, right? So that's probability theory is about such kind of thing. And let's take an example here. Let's think about the weather as a variable. Okay, we are going to consider weather here. And we're going to think about 4 different cases for the weather. Whether it's sunny, rainy, cloudy, and snow. And P means probability. So what is the probability that weather is sunny? And what is the probability that weather is snow, rainy? Things like this, right? So this probability is simply a probability of such a case. Simply a probability that weather is snow. So how do you calculate this probability? Okay, let me ask you a question. What is the probability that weather is sunny in general? And how do you calculate? So this question is same as, let's say I throw a dice. The dice like this, right? What is the probability that you're going to get 1? What is the probability? How do you know? How do you know? You know that it's 1/6, right? How do you know? It's simply the number of cases you have divided by the total case. Now then, what is the probability that weather is sunny? Same thing actually. Maybe you can see that, okay, we have 365 days a year, and you can count how many days you have sunny. Maybe, I don't know, maybe in a year, maybe 100 days are sunny. In that case, what's the probability? Maybe you can say this is the probability that weather is sunny. You can count it that way, right? Same as this one. So this probability is like this kind of thing. So what is the probability of rainy? You can count the number of days with the rain. Same for the snow, same for cloudy. Okay? So simply this probability is the probability of each event. This is the same thing, right? What is the probability that dice will show you 1? That is the probability of this event, only this event, divided by total event. So this is how you calculate the probability for each event. For the variable, sometimes we have discrete random variable. Discrete variable, sometimes we have continuous variable. The dice, this is a discrete, because the total case is only from 1, 2, 3, 4, 5, 6. That's it, right? In this case, again discrete, because I consider that weather is only 4 of them. Sometimes, right? Sometimes the weather can be like sunny plus rainy kind of thing. But I don't consider, I'm not saying that that's not, I'm not interested in those things. I'm only interested in 4 different weather. Okay? In my mind, weather is only 4 of them. So it's like a quantization, kind of. Okay, I quantize the total, all the weather into 4 different things. I classified it this way. Okay, so that's how you do it, discrete random variable. However, in random variable, sometimes you can have a continuous random variable. For example, temperature. Temperature can be continuous, right? From certain degree to another degree, it can be continuous. So depending on the event, sometimes discrete, sometimes continuous, but that's the probability. So as you see here, when you throw the dice, each event will be 1/6. We already know that, right? So that's the probability. That we call as a prior probability. So we have two different probabilities: prior probability, posterior probability. So prior basically means that the probability we already know, right? We already know. 1/6, we already know that, right? So that's the probability. And what about this? Is this prior or posterior probability? This is a prior probability because we already know that. Okay? Because we can count it. We know that, right? So all of these things is a prior probability. Based on a certain knowledge, we can calculate the probability. So that's the prior probability. Then what is the posterior probability? Posterior means you can calculate the probability after something, right? After evidence. So simply speaking, the posterior probability is something like this. It's conditional. So let's see, P, A given B. This is a conditional probability, right? What does this mean? P, A given B. This basically means that B event already happened. And given that, what is the probability of A? That's the posterior probability, right? Because B already happened. And then the probability of A. Clearly, this one is very different from A. It's very different from, this is not same, right? This is not the same. So this is what we call as a posterior probability. For example, this one. This one actually means that when you throw a dice, depending on what value you have in dice, you may have a different price. So that's what they mean. But I think this is not a very good example. But we're going to see this posterior probability many times. For example, this one. There is a concept of total probability here. Another probability, but total probability basically means that when you think about all the cases and add up all together, that is the total probability. So for example, right, think about the dice. We have 6 different cases. Dice will give you 1 or 2, 3, 4, 5. We know that, right? And the probability of P, probability that you're gonna get 1, probability that you're gonna get 2, probability that you're gonna get 6, and when you add it all together, what's gonna be? 1, right? Because this is a total case. That is a total probability. Now in here, the total probability tells you that probability of B, whatever B means, probability of B equals that probability of A can be many things, but probability probability of A times A given B, right? The probability of B given A, actually. Probability of B given A and times BA. We know this one, right? These two are the same thing. Do you know this? We learned this one before, right? In another course. So this basically means that probability of B is the same as probability B given A times probability of A. Let's think about an example here. Let's think about that A. This is something like this. I don't recall a good example here, but let's say A is the probability. A is the probability that weather is sunny. Right? Just example. I'm talking about this one. B. No, this. Okay. Let me put it another way. Let's say B is the case of weather is rainy, and we have. In this case, you are considering many different AI. So like this: A1 plus A2 plus AN this is what you have here, right? So as an example, let's say A1 is a sunny. In our previous weather example, let's think about this way as an example. For weather, in my definition of weather, we have only 4 different weathers. I don't have any other weather. Okay? Weather is only one of these 4. Okay? This basically means that what is the probability that we have rain in general, right? What is the probability that you have rain for the day? That's the probability. In order to calculate that probability, what you can do is that first you can calculate the probability that's sunny for one day. And then this one basically means that when you have sunny, what is the probability that what is the probability that you have rainy for the next day? Something like this, right? And this is the case that you have a cloudy for one day. And when you have cloudy one day, what is the probability that you have a rainy for the next day? So this is all the possible cases, right? Let's say you have what I want to find out is the probability of rain today. Okay? How do you calculate? Let's say tomorrow. Let's say you want to estimate what is the probability that you have rain tomorrow. But you never know because tomorrow is the future. How do you know, right? You never know. But let's say you're going to estimate. So how do you estimate? We can look at the weather today. Okay? Think about this is common sense that let's say today we have a very sunny day. What's going to be the weather tomorrow? Do we have snow tomorrow? No. Suddenly? That is very, very unlikely, right? Very unlikely. Maybe, but very unlikely. Most likely we have another sunny day tomorrow, right? But maybe there is a probability that today is sunny, but tomorrow is rainy. Maybe the probability is 10%. Maybe, right? That's this percent, 10%. The probability that today is sunny, so tomorrow is again sunny, that probability is pretty high, right? That's pretty high. So we're going to consider all these cases. So what is the probability that today is sunny, but tomorrow snow? What is the probability that today is sunny, but tomorrow rainy? Sunny today, cloudy tomorrow. So all these different cases. And add it all together, right? In that case, once you do this, now you're going to have the probability that we have a rainy tomorrow. So that's the total probability. Okay? But the reason that we are going to rewrite this equation into this way is that typically this equation, this probability, and this probability is very easy to get, but this is very difficult to get. Okay? So that's why we use this kind of equation. Actually, in this example, maybe it's not a good example because, forget this example. I'm saying this is not a good example because, the here and here, this is not easy to get, right? Again. So, but in general, when you use this equation, each one of these is very easy to get, but this is very difficult to get, typically. Okay? So that's why we are not going to calculate this one as it is, but we are going to change it into this way, and then we're going to get each one of these and doing this calculation instead. So that's what typically do. So general theory behind this is called the Bayes rule. Okay, Bayes rule. So this is the Bayes rule here. What this Bayes rule tells you is that actually when you bring the PA here, what you're going to get is P B given A times PA equals P A given B PB. So that's what it means. That's what it means. So this is again conditional probability with the multiply with this, right? At this point, this does not really make sense to you, but when you go to the next one, as an example, it's a little bit easier to understand. So let's move on to the next one. In probability theory, you're going to look at this word many, many times. Hypothesis. You're going to hear the hypothesis. Hypothesis. Hypothesis basically means that there's no clear thing. You're going to just estimate. That's what hypothesis means. Okay? So we have probability of hypothesis. This D is the observed data. Okay? So you have some probability of observed data. This is the probability of hypothesis. So given the hypothesis, what is the probability of drained data? Eventually, you want to calculate this one. So this is what you are going to calculate eventually. So what this means is you already observe some data. Based on that, you are going to estimate the result. So that's the hypothesis. Example is this one. So let me tell you example here. The question says, this whole story actually is very easy to understand. I mean, the problem of this kind of course and the problem of the whole thing is that once you understand, it's very easy, but all of these word and hypotheses, for example, all this terminology looks difficult, right? When you look at this equation, you're going to get a headache because this equation, this means this word doesn't seem to have a meaning. But once you understand based on the example, that's pretty easy. So let's take a look at question. The question is, the title says diagnosis. So let's think about that you are a doctor, medical doctor, right? So you're going to get a patient. So since you are a doctor, when you look at the patient, the first thing you need to do is diagnosis based on what he tells you, right? Patient will come to you and say, oh, I have a headache, right? Something like this, right? He's going to tell you why he come and see you, right? So based on some symptom, that's what he calls a symptom, right? He's going to tell you the symptom. Based on the symptom, you're going to diagnose him, right? What would be the problem and things like this. So now, the question is, what is the probability of this one in the patient with stiff neck? This one, I don't know how you call it, meningitis. So this is one of the symptoms. That's the symptom that you have some problem in the brain, but in the real brain here. So that's one of the disease. But stiff neck means that you have a stiff neck here, right? So let's think about this way. You're a doctor, a patient comes to you, and the patient says, oh, I have stiff neck, right? Oh, I have stiff neck, like this. That's the symptom that the patient will tell you. Then as a doctor, how would you diagnose? That's the problem. There are so many different symptoms or so many different diseases that is related to with the stiff neck, right? So simply, let's say patient tells you that, oh, I have stiff neck, then how would you diagnose? It's pretty difficult, right? So the probability that the patient has a stiff neck, what is the probability that you're going to diagnose him with this disease? That's this question. Okay, let me think about another way. Let's say the patient comes to you and say, oh, I have a cough. I have a cough. Then what would you say? You're going to diagnose him. After diagnosis, you're going to give him some medicine, right? So the patient says, I have a cough. Then how would you diagnose? Maybe you can say, oh, you got a cold. Then why do you say that? How do you know it's cold? Maybe cough comes from some other disease, right? So how do you know? Why do you say you're going to get cold? Because the probability, this is all probability. Probability that the patient has a cough and this patient has a cold, this has a high probability, right? The probability is pretty high. When a patient has a cough, he's going to get cold. It's all probability. Same thing, that's what I'm talking about here. Let's say a patient has a stiff neck. So how many patients with a stiff neck will have this disease? So that's what it means. What is the probability of meningitis in the patient with a stiff neck? Same question, actually, right? So that's the question. So here, S means a symptom, like a cold, like a cough, for example, right? S means symptom, M means disease, but this one you can say hypothesis. So let's say, in this case, hypothesis is like a cold. Okay, meningitis is different word, so let me change this one. Let's say, what is the probability of getting cold in the patient with a cough? It's something like this, right? So cough is a symptom. And getting cold is hypothesis. As a patient, as a doctor, you're going to get a hypothesis. You're going to make a decision as a hypothesis, right? But symptom is getting cold. The symptom is cough. Right? So here it says a doctor knows that this disease causes the patient to have stiff neck in 50% of the time. So this word means the opposite way. So this means that when someone has this disease, 50% of the people will have stiff neck. The question is the reverse one. If the patient has stiff neck, what is the probability that he has this disease? Whereas this question is the opposite way. If you already have this disease, 50% of the people will have stiff neck. So these two are different. You know what I'm saying? So this one, the original question is like this. You have a cough. What is the probability that you already get a cold? So that's the question. The second thing is that if you have a cold, what is the probability that you have a cough? So that's the different thing. This one is pretty easy to get. How do you get? Let's say you have this disease. Among the people who has this disease, 50% of the people have stiff neck. This one, you can easily get it. Let's say, let me change it another one. 50% of the people who have cold will have a cough. We can easily get it, right? Let's say we have 1,000 people. All of them have a cold. And you can easily count it. How many people have a cough? Then you're going to get this, right? So this one is easy to get. Because you are going to collect the people with this disease and ask them how many people you have a stiff neck. So you can ask them. So you can easily get this probability. And this probability means that probability of this disease. This one also you can easily get because you can count how many people you have, how many people has this disease. Out of those total population, how many people has this disease? It's easy to get, right? You can do survey, no problem. This one, again, this is easy to get. You can count how many people has stiff neck. Again, you can do survey, no problem. So this one easy to get. You can just count how many people have stiff neck. This one again, you can easily count how many people have this disease. These two are easy to get. So we call these two are prior probability. Prior probability. And this one also you can find out easily. Because out of these many people who have this disease, you can ask them how many have a stiff neck. So you can easily get this one again. So once you get this three, now then using this three, put it together like this in the equation, in Bayes' rule, now you can find out this one. This is what we want to get. And typically, this is not easy to get in general. So that's why using these three and put them together like this, we're going to calculate this one. That's what we are trying to do here. Okay. So same thing for this hypothesis. This hypothesis, same thing. What you're going to do is that you have a D. D means data. That means a symptom. H means hypothesis. So you're going to make some decision here. Because what we are talking about is a decision block. So your decision is based on the hypothesis. So in order to make a decision, you need to get a data. Based on the data, you're going to set a hypothesis. So based on the hypothesis, you're going to make a decision. Okay? So that's how you're going to get here. Let me just move on to here. Okay, let me briefly talk about this one. So this slide tells you that, let's say the probability of cancer. Probability of cancer. This is easy to get, right? You can simply count how many people have cancer out of population. Let's say the population is 1 million, and how many people has cancer? That's the probability. And this probability is like how many people are not under cancer. So again, simply count it, right? So this one, this probability is basically when you add these two, it's going to be 1. Because this is the probability that with no cancer, this is the probability with cancer. Is it easy to get? What is this one? That basically means that you actually have a cancer, because this is the probability that someone has a cancer, but someone is diagnosed as a cancer. This one is the probability that there is a cancer actually, but it says negative. So the cancer was not detected. There is actually cancer. Let's say someone has a cancer, but doctor said, oh, you don't have cancer. That's the probability. Right? Given that you have cancer, the probability of negative. Similarly, in this case, there is actually no cancer, but doctor diagnosed it as you have cancer. Positive, right? You are positive, but actually negative. That's this probability. This one is like you are negative, but you are diagnosed as negative. So each one of these is all probability. When you put these together, think about this way. This basically means that this is the probability of cancer, positive cancer. And when you have a cancer, this is the probability that you are diagnosed as a cancer. So that basically means that you have a cancer, but given that you have cancer, you are diagnosed as a positive. This basically means that no cancer, but given that there's no cancer, you are diagnosed as positive. So when you add these together, this is simply a multiplication. Let's say you get this probability, and you are going to add these two. You're going to plus these two. Then what is the probability? This is the probability that you're going to get a positive result. Simply speaking, this is the one. Let's say you go see a doctor. Okay? You don't know you are cancer or not. Right now, you don't know anything about yourself. Now you go see a doctor, and doctor basically do some test, do some check, blood test, all these things, right? And based on the probability, doctor tells you, oh, you have cancer. Okay, you are positive, let's say. Then now the question is, do you believe him 100%? That's what I'm saying. Do you really believe that doctor says you have cancer, but do you believe really 100%? Do you think he's completely right? Maybe not. What he said is maybe true, may not. May or may not be true. It's always based on probability. He's going to make a decision based on the probability. Okay? Probability. So this is all probability. So in this example, right? In this example, what is the probability that you're going to get a positive result? You're going to add these two. Let's add these two. In this case, it's about 3.7%, right? If you hear that, oh, you are positive in cancer, the probability that you are actually the probability that you are hearing that you are positive is only 3.7%. That's what that means. Because here is the probability that you heard positive, but actually you have a cancer, actually you don't have. So when you have actual cancer, but you get a positive, you actually don't have it, but you get a positive. So you're going to consider these two. There are only two cases. Maybe you have a really cancer, or you have no cancer. There are only two cases, right? Considering these two cases, but you heard that you have a positive, so you're going to add these two. Then it's going to be about 3.7%. So the probability that you hear a positive cancer is only 3%. Why is that? That's because that number of people in cancer is so low. So low. So this one actually is just simply a normalization. You have this about 0.7%. This is almost 3%. So including these two and adding these two and normalize it, then I'm talking about the ratio between these two. Only between these two, right? The ratio is, this is about 20%, this is about 80%. Only think about these two. That's simply a normalization. Okay? Yeah. Okay, so let's continue next time.